The hot surface of the sun radiates electromagnetic energy that spans the entire spectrum. The intensity of the light is greatest in the visible portion of the spectrum, and the warmth we feel on a sunny day is due to the absorption of infrared radiation. That warmth is energy. Conventional solar power uses that energy to heat water. The solar cells we will be discussing here convert that energy directly into electrical energy. It doesn't have to be a hot day. All we need is light. A clue to how they do this can be found by looking at the spectrum. A close look at the spectrum produced by the sun reveals thin darkened lines in the rainbow of the visible colors. These darkened lines are caused by atoms in the sun's and the Earth's atmosphere absorbing precise energies of light. These patterns of lines, like fingerprints, are called absorption spectra. The understanding of how atoms absorb and emit light reveals secrets of the electronic structure of the atom and is crucial for our discussion of the modern silicon solar cell. Niels Bohr proposed the first successful model of the hydrogen atom in 1913. It was a simple planetary model like the Earth orbiting around the Sun. A light negative electron in a circular orbit around a heavy, nearly stationary positive proton. Instead of a gravitational force, an attractive electric force holds the electron in its orbit. In order for the model to work, Bohr had to make a radical proposal. The electron can only occupy certain stable orbits with prescribed energies. The electron orbit closest to the proton has the lowest energy. Energy is needed to pull or lift the electron away from the proton, so orbits with larger radii have higher energies. If an electron is to jump from a lower orbit to a higher orbit, it will require an energy source. The energy source? Light. The electron can absorb a photon of light and use all of that photon's energy to jump from a lower energy orbit up to a higher energy orbit. Conversely, when the electron falls, it will emit all of its extra energy as a corresponding photon of light. It is simply conservation of energy. The energy of the photon is completely absorbed by the electron, allowing it to jump to the next energy level. Only particular photons can give their energy to the electron. That photon's energy must exactly match the energy required for the electron to jump. You may remember that there is an inverse relationship between energy and wavelength. So we say that the electron absorbs a particular wavelength or color of light in order to gain the energy required to jump energy levels. Let's look at an example. Say that the electron is in the second energy orbit. It can absorb the energy of a red photon and jump to the third energy orbit. When it falls back to the second level again, it must emit a red photon such that the total amount of energy remains the same. Similarly, an incoming blue photon will excite the electron into the fourth energy orbit. If the electron falls back, it will emit a blue photon, and so on. The result? The hydrogen atom can absorb photons of light with particular wavelengths, or energy, and it can also emit photons of light with those same particular wavelengths. So for an excited hydrogen atom, we would expect to see particular wavelengths of light produced as the electron falls back and emits photons of light corresponding to those energies. This emission spectra of hydrogen is exactly what we see. Notice that only particular wavelengths of light are emitted, wavelengths that correspond to the required amount of energy to jump between levels. Furthermore, Bohr was able to calculate the exact wavelengths of the spectral lines of hydrogen in the visible region of the electromagnetic spectrum. What does this have to do with the sun? The dark lines we have seen in the sun's spectra are direct evidence that hydrogen atoms are absorbing energy from the sunlight. Why? Because they match, line for line, the emission spectra of hydrogen produced in the laboratory. These spectral lines become a valuable tool that we can use to learn about the electronic structure of the atom. However, while Bohr's model was extremely successful of predicting the wavelengths of light in the spectra of hydrogen, it failed to predict the light spectra in an atom with more than one electron. That success would have to wait for the birth of quantum mechanics. The first papers that describe quantum mechanics were published in 1926. They not only gave us a description of the atom when more than one electron is involved, they completely revolutionized physics and chemistry. The atoms of elements, other than hydrogen, contain 2 or more positive protons and an equal number of negative electrons. The number of protons identifies the element. You may recall that the positive protons are located at the compact center of the atom called the nucleus. Also in the nucleus are the electrically neutral particles called neutrons that will not enter into our discussion here. The electrons can be thought of as filling diffuse shells that surround the nucleus, similar to the orbits of the Bohr atom. The first shell can hold up to 2 electrons. The second and third shells can each hold up to 8, and so on. The modern photovoltaic cell consists primarily of silicon atoms. An atom of silicon has 14 protons. Of its 14 electrons, 2 fill the first shell, 8 fill the second shell, leaving 4 in the third shell. These 4 outer electrons are called valence electrons. They are important because they are involved in interactions with other atoms, as in the case of chemical bonds. But ordinary silicon will not help us capture and use the energy of the photons coming from the sun. We will need 2 other elements that are close in their electronic structure to silicon. The first is boron. An atom of boron has 5 protons and 5 electrons, 2 filling the first shell, leaving 3 valence electrons in the outer second shell, 1 less than silicon. The second is phosphorus. An atom of phosphorus has 15 protons and 15 electrons, with 5 of these valence electrons, 1 more than silicon. If we bring 2 atoms close together, the valence electrons from each atom will be attracted to the positive nucleus of the other atom. Pairs of valence electrons get shared between the atoms, 1 from each atom. This is the basic idea of a covalent molecular bond. Molecules are often represented with ball and stick models. The balls represent the atoms, and the sticks represent the bonds formed between their valence electrons. Molecular bonds not only hold atoms together to form molecules, but they are also responsible for holding atoms together in a covalent crystal. An example of a covalent crystal is a crystal of carbon. It has 4 valence electrons and crystallizes in a tetrahedral pattern, forming a beautiful gem, the diamond. Silicon, too, has 4 valence electrons. In a silicon crystal, each atom bonds with 4 neighboring atoms in a tetrahedral pattern. True, the silicon cell may not be a beautiful gem, but a crystal of silicon forms the jewel of modern electronics and our photovoltaic cell. For our discussion, we will simplify the representation of the silicon crystal. We represent the three-dimensional crystal flattened to 2 dimensions. Each silicon atom, with its 4 valence electrons shown, is bonded to 4 other atoms. If we view our flat crystal along the edge, we see what appears to be a simple row of silicon atoms. Pairs of valence electrons form the covalent bonds between the atoms. Collectively, they form the valence band. Unoccupied atomic orbits with higher energy merge to form the conduction band. These 2 bands are separated in energy, much like the regions between the allowed orbits in the Bohr model of the atom. This energy difference is called the band gap and refers to an energy interval where no electron is stable. Since the silicon atoms in the crystal are electrically neutral, we will indicate this neutrality by graying them out. Now, let's shine a light on our silicon crystal. If the incoming photon's energy is insufficient, the electron will stay in the valence band. However, if a photon of light has sufficient energy, a valence electron can absorb that photon, jumping up into the conduction band. It just so happens that such photons are abundant in sunlight. When sunlight strikes the silicon crystal, the photons are absorbed by the valence electrons, promoting them to the higher energy conduction band. Why do we want electrons in the conduction band? If electrons are in the conduction band, they are free to move and therefore can carry an electric current. Now, because the region the electron left behind was originally electrically neutral, the loss of the negative electron leaves this region positive. The positive region is called a hole. We will color it red for its net positive charge. Remember, electrons are colored blue here to designate their negative charge. Note that the crystal is still overall electrically neutral, with the same number of positive charges and negative charges. However, electrons, once promoted, can spontaneously fall back into the hole in a process called recombination. If we are to use the energy of the electrons, now promoted into the conduction band, to power our electrical devices, we must first separate the electrons from the holes before they can recombine. We can accomplish this with an electric field. A simple example of this would be connecting a battery across the ends, say a positive terminal on the left and a negative terminal on the right. The positive terminal will attract the mobile conduction electrons so that they will move toward the positive side. At the same time, valence electrons move to fill the holes, leaving new holes behind. The result is that the holes migrate toward the negative terminal, and we have an electric current. But a crucial point for our solar cell is that we don't need a battery to create our electric field. A modern solar cell incorporates an intrinsic electric field that will separate our charges, giving us the current we need. So how do we create this electric field? A modern solar cell uses a p-n junction. Look again at our flattened, electrically neutral silicon crystal. We again show this neutrality by graying it out. Doping is a process where small numbers of impurity atoms replace some of the silicon atoms in the crystal. One can make N-type silicon by adding impurities, such as phosphorus with 5 valence electrons, one more than silicon. When in the crystal, 4 of its valence electrons form complete bonds with neighboring silicon atoms. This leaves 1 extra valence electron that will orbit the phosphorus in a Bohr-like orbit at very low temperatures, but will diffuse through the crystal at ordinary temperatures. A phosphorus atom is called an electron donor because it donates an extra electron to the silicon crystal. Because the phosphorus atom has 1 more proton than silicon, it has a net positive charge. We will color it red to denote this extra positive charge. One can make p-type silicon by adding impurities, such as boron, with only 3 valence electrons. It forms only 3 complete bonds with the neighboring silicon atoms, leaving 1 incomplete. This incomplete bond has the ability to capture an electron, usually a nearby electron from the valence band. This neighboring electron leaves behind a positive hole that can diffuse through the crystal at ordinary temperatures. With an extra electron near the boron, the region has a net negative charge. Because of this, the boron is called an electron acceptor. We will color the boron atom blue to denote its net negative charge. A p-type and an n-type silicon in contact with one another form what is called a p-n junction. Electrons from the n side diffuse across the p-n junction to the p side, and holes from the p side diffuse across the p-n junction to the n side. The electrons and holes can then recombine. The result is a net negative charge on the p side of the junction and a net positive charge on the n side, creating a strong electric field across the junction. Now, when we shine light at our p-n junction, an electron will be excited from the valence band into the conduction band, leaving behind a hole. This time, however, before the hole and electron can recombine to emit a photon, they are separated by the electric field created by the p-n junction. The negative electrons move to the positive region, and the positive holes migrate to the negative region. By separating the electrons from their holes, we have prevented their spontaneous recombination and loss of their excitation energy. Now we have all of the pieces required to construct our silicon solar cell. We start with a metallic layer, which serves as an electrical contact and as a substrate to support the rest of the cell. A thin wafer of boron-doped p-type silicon is laid down. Phosphorus is then diffused into the top surface, forming a p-n junction very near the top. With the p-n junction near the top, most of the sunlight will easily reach the junction. An anti-reflective coating is sprayed on the front surface to cut down on lost reflected light. Finally, front surface contacts are made to collect the electrons arriving from the junction. This grid is constructed with as few contacts as possible so that the p-n junction isn't shadowed too much. We can now power a light bulb or electric motor by completing the circuit. Our cell is complete. Photons of sunlight pass through the thin N layer. In the junction, their energy can be absorbed by electrons and excited into the conduction band, leaving behind positive holes. But before these can recombine, The electric field in the p-n junction separates them. The electrons move toward the front surface, and the holes move toward the back. Then they travel through the load and around to the bottom of the solar cell. The number of electrons that leave through the front contact is equal to the number of electrons that return to the back contact where they recombine with the holes. As more photons of sunlight are absorbed, electrons are excited into the conduction band and the process is repeated. No electrons are used up in the process. Photons give up their energy to create electron-hole pairs. The electrons give up their energy in the form of electrical power and return to the back contact of the cell where they finally recombine with the positive holes. It is simply conservation of energy, and the silicon solar cell should work in principle indefinitely. With no mechanical parts to break down, solar cells have operated in practice for 25 years or more.